In module 4 of chapter 10, we shall learn about special theory of relativity as an application of differential geometry. In 1905, Albert Einstein developed the special theory of relativity as an application of differential geometry. The special theory of relativity depends on two postulates, two main postulates. The first one is the principle of relativity and the second one is the invariance of the velocity of light. Now, in special theory of relativity, we shall learn three things, that is Lorentz transformation. The second one, the space-time geometry of special theory of relativity, that is Minkowskian metric, and third one, the null cone coordinates for Minkowskian metric. So, let us start with the Lorentz transformation. So, in module 4 of chapter 10, it is entitled in this way, the inside geometry of the special theory of relativity. Here we shall learn about Lorentz transformation, Minkowskian metric and special theory of relativity in null cone coordinates. Now, in 1905, Einstein formulated the special theory of relativity. At that time, physicists had the opinion that there should be time difference for the light rays to come from the sun to the earth when light moves along the motion of the earth and perpendicular to the motion of the earth. Generally, we consider that if one thing is travelling from one space to other, it takes some times. So, physicists believe in that way, that the light rays come from sun to the earth should take some time, but actually this does not happen. Einstein formulated the Lorentz transformation between two inertial frames moving with constant relative velocity, assuming that two following postulates. Actually, special theory of relativity is totally dependent upon these two postulates. The principle of relativity, it states that all physical laws assume the same form in all inertial frames of references which are moving relative to each other with constant velocity. That means, that all laws, all physical laws will have the same form in all inertial frames of references which are moving relative to each other with constant velocity. That means, the relative velocity between two frames, if one frame is denoted by s and another frame is denoted by s dash, then the physical laws will take the same form. And the second one is that invariance of the speed of light. The velocity of light does not depend on the relative motion of the source and the observer. It is an invariant quantity. In general, the special theory of relativity, the shape of a body changes from one inertial frame to the other. For example, a sphere in one inertial frame will appear as an ellipsoid in another frame. Now, let us see the Lorentz transformation. Now, from Euclid's postulates, we know that the distance between two neighboring points whose coordinates are p x y z and q x plus dx y plus dy z plus dz in 3 dimensional space. It is an invariant quantity and we have this expression. In our previous chapters we have discussed about this. Dl square equals to dx square plus dy square plus dz square. Now, as Einstein formulated the special relativity in the 4 dimensional space time, so we can consider in this form dx square plus dy square plus dz square plus lambda square dt square, and it is an invariant quantity where lambda is a constant having dimension of velocity, that is due to invariance of dl square under any coordinate transformation, lambda is an invariant notion of velocity and dt is the time factor here. So, for 4 dimensional space we have x, y, z and t. X, y, z is the space coordinate and t is the time coordinate. Now, although we are using the space and time on the same footing in 4 dimensional space time, but still there should be some separate identity for the time coordinate, and to realize this one we modify the equation by this quantity ds square equal to dx square plus dy square plus dz square minus lambda square dt square, and assuming that ds is an invariant quantity, and here we see that this ds is called the metric of the 4 dimensional space, and it is not a positive definite because this quantity minus lambda square dt square. Now, we consider the 2 reference frame, one is S frame with coordinate system x, y, z, t, and another one is S dash frame with the coordinate x dash, y dash, z dash and t dash. And S dash frame is moving relative to S with a constant velocity v along the common x dash axis, and y and z axis of the 2 frames are parallel as shown in the figure, this one. So, for the first one it is a S frame and for the second one it is S dash frame, and S dash is moving with a constant velocity v along the direction x dash. Then the explicit form for the transformation equations are x dash equal to x minus v t by root over 1 minus mu square, y dash will be equal to y, z dash will be equal to z, and t dash will be equal to t minus x b by lambda square by 1 minus mu square under the square root. Now, these transformations are known as Lorentz transformation. We can deduce this one x dash and t dash from the above relations, and this is known as Lorentz transformation, where the absolute velocity lambda is identified as the velocity of light. So, this lambda becomes the velocity of light. Now, by this Lorentz transformation we have some important relation, that the quadratic expression s square equal to x square plus y square plus z square minus lambda square t square is an invariant quantity under Lorentz transformation. That means, it remains invariant under the Lorentz transformation. The differential form also transform according to Lorentz transformation. Now, this is a very important thing, that due to Lorentz transformation time dilation and length contraction occur. That is, a moving clock will go slow compared to that in rest frame, and length of a rod appears to be contracted when it is seen from S frame. So, these two things occur due to the Lorentz transformation, and it is very unique thing in the special theory of relativity, the time dilation and the length contraction. In the previous section, we have seen a very important transformation called Lorentz transformation in special theory of relativity. Now, in next section, we shall learn about the space time geometry of special theory of relativity and a Minkowskian metric. Now, here we shall learn about the light cone, and from that light cone we shall see that what is future light cone, what is past light cone, all these things. Lastly, we shall learn special theory of relativity in null cone coordinates, and here we shall see that Minkowskian metric is invariant under the scaling, and we shall find the scaling factor. So, let us start with the space time geometry of special theory of relativity. So, in this section we learn about the space time geometry of special theory of relativity and also the Minkowskian metric. Now, this section deals with the geometry of the 4-dimensional space time of Feinstein's special theory of relativity. We have seen that the quadratic expression s square equal to x square plus y square plus z square minus lambda square t square is an invariant quantity under Lorentz transformation. In our just previous slides, we have obtained this one. Now, as s square is indefinite in sign, so we shall explore all three possibilities, namely when s square greater than 0 or s square equal to 0 or s square less than 0. Now, we start with s square equal to 0, that is x square plus y square plus z square minus lambda square t square equal to 0. So, from that equation we get that it is a cone in 4-dimensional space time with vertex at the origin 0 0 0 0 and t axis as the axis of the cone. The observer is situated at the vertex O. We shall see in the next slide in the figure. For all space time points inside the cone, s square will be less than 0, while space time points outside the cone will be s square greater than 0. Now, from the last expressions we have s square equal to lambda square t square in the second bracket 1 by lambda square under the first bracket x square plus y square plus z square by t square minus 1, and that can be written as lambda square t square u square by lambda square minus 1. So, this is the figure that at the O the observer is sitting there, and above the O, that means the upper part of that cone, it is called the future cone or future null cone, and the lower part is called the past null cone. Now, the particles inside the cone will have s square less than 0, that is u less than lambda, and u is greater than lambda for particles outside the cone, and u equals to lambda when particle is on the surface of the cone. The upper half of the cone is called the future null cone, and the lower part is termed as past null cone, and the total thing is called null cone or the light cone. Now, in relativity theory, the space time geometry is not Euclidean, rather it is pseudo Euclidean, or it is known as Minkowskian geometry. In the notation convention of Einstein, we write the space time interval as d square equal to g mu nu dx mu dx nu, where mu nu is running from 0 to 3. In our previous chapters, we have this expression, which is the fundamental form for a Riemannian space. So, we can express d square in this form. Now, if x 0 equals to lambda t, x 1 equals to x, x 2 equal to y, and x 3 equal to z, then g mu nu is termed as a metric tensor, which is a 0 to symmetric tensor and is represented by a 4 cross 4 matrix, as the dimension is 4. So, it is a 4 cross 4 matrix, and for special theory of relativity, the metric tensor is termed as Minkowskian metric, and this g mu nu have this matrix. The diagonal elements are this one -1, 1, 1, and other are zeros, and we can write the above matrix in this form also, g mu nu equals to diagonal -1, 1, 1, 1. Now, if a mu are the components of a 4 vector in Minkowskian space, then its length will be defined as g mu nu a mu a nu, and it will have this type of expression a 1 square plus a 2 square plus a 3 square minus a 0 square. And the scalar product between two 4 vectors a and b is defined by in this way g mu nu a mu b nu, and this will be a 1 b 1 plus a 2 b 2 plus a 3 b 3 minus a 0 b 0, where mu nu is running from 0 to 3. Now, see that if the length of the vector is less than 0, that means norm of a mu square is less than 0, then the 4 vector a mu is called a time like vector, while when the norm of vector, that is a mu norm square, is greater than 0, it is called space like vector, and we termed a mu as the null vector if norm of a u equals to 0. Now, in non-Euclidean geometry also, a null vector is distinct from 0 vector. A vector having all components identically 0. 0 vector means a vector having all components identically 0. A 0 vector is a null vector, but a null vector is not a 0 vector. In our previous chapters, we have discussed thoroughly about these things with examples, that a 0 vector is a null vector, but a null vector is not in general a 0 vector. Now, in special theory of relativity, we have null cone coordinates. Here we consider for simplicity the two dimensional Minkowskian space time d square equal to minus dt square plus dx square, and we can express this one as GAB dxa dxb, where GAB is diagonal minus 1 plus 1 with AB is running from 0 and 1. So, we have only two coordinates t and x. Now, if we transform this t and x in terms of u and v by this relation, u equals to lambda t minus x and v equal to lambda t plus x, then the Minkowskian metric can be written as d square equal to minus du dv. So, the above expression, the GAB will be 0 half half 0. With AB is running from 0 and 1 and x 0 equals to u and x 1 equals to v. Here u v are null coordinates and are usually termed as null cone coordinates, and GAB in the bracket n is called Minkowskian metric in null cone coordinates. From equation 48, it is clear that the Minkowskian metric is invariant under the scaling of the null coordinates, as if we transform as mu tilde as mu u and v tilde as 1 by mu v. So, mu is the scaling factor, we can easily obtain the value of the mu as follows. Now, as d square is invariant under the above scaling, so the transformation can be considered as a Lorentz transformation, and mu is a function of the relative velocity. The Lorentz transformation x tilde t tilde from x t is obtained from the 42, considering mu as V r by lambda, and using the Lorentz transformation t tilde equals to t minus V r x by lambda square by root over 1 minus V r square lambda square, and x tilde equals to x minus V r t by root over 1 minus V r square lambda square. With V r the relative velocity between the two inertial frames. So, u dash takes the form lambda t dash minus x dash equals to lambda t minus V r x by lambda by root over 1 minus V r square lambda square minus x minus V r t by root over 1 minus V r square lambda square. That means, we have replaced the value of t dash and x dash, and simplifying we get u dash equal to u under the root 1 plus V r by lambda by 1 minus V r by lambda. And similarly, V dash have the expression equals to V root over 1 minus V r by lambda by 1 plus V r by lambda, and the mu has the value this one root over 1 plus V r by lambda by 1 minus V r by lambda. So, the scaling factor mu has this expression. In module 4 of chapter 10, we have learned about the application of differential geometry in special theory of relativity. Here we have learned about the Lorentz transformation. Secondly, we have learned about the Minkowskian metric and the space time geometry for special theory of relativity, and lastly we have learned the geometry in null cone coordinates. So, with these things we end this module.